Ah.
1, 2.
Ah.
1, 2, 3.
Oh God, this is good. We're going to talk about the seventh today, and how possibly God is one and rests on the seventh.
But before we do, I want to show you something I found in the other trailer. Because we're going to be talking about the D circle, the every 369 D circle, or the every 24 D circle that has the 369 in it. And I want to show you, go this way. I made this back when I first discovered the D circle. Oh, it's too big to even get in the picture. But this is what we're going to be looking at today. It starts with 0, 1, 1, 2, 3. And then when I first discovered, and this was done, I'm going to have to turn it sideways to give you the date. It's at the very bottom here. You have to read it upside down. I signed it. Burton James Fennison, Christmas morning, 2020. That's 2020. And then I signed it right there, and it's faded. I'll have to re-sign it. But yeah, I made this chart when I first. So honestly, this did happen at 4 o'clock in the morning, sitting under my sister's Christmas tree in Vancouver, Washington. So you know what that makes this that we're going to study today? Okay. This is the 24 wheel. This is a design I made to highlight a pattern I found under one Christmas when I spent a Christmas with my sister in Vancouver. And I woke up early, and I was under the Christmas tree trying to figure out a continuous 369 pattern in the 24 wheel. And now I see it's online. Someone else has also found this. I saw it posted by Jane108. It makes a unicursal, which means uni is one. Cursal is like cursive writing. One line, unicursal hexagram that goes from 3 to 6 to 9, and I'm going to tell you why that 0 is actually a 9. Back to 3, and back to 6, and back to 9. I thought, whoa, it's just a continuous motion of 369, 369. Of course, it makes everybody think of what Tesla said, but I don't know if he said that or not, actually. But what I want to point out that I haven't seen online yet is on either side of this continuous 369. Well, first let's talk about why that turns to a 9. And that's important for what the 24 circle is doing. I'll show you that in a minute too. As it's going in this continuous circle every 24, it comes all the way around to here, and then the 8 plus the 1, click, make it a 9. See that? 8 plus the 1, click, make it a 9. So in its original format, it adds up to 108, okay? But then once that clicks over to be a 9, it adds up to 117. And that 9 ends up being very, very critical to whatever this particular program, I'm just going to say it, they're programs, folks, is doing. Because we're going to talk about the seventh today, and how possibly God is one and rests on the seventh. And of course, I'm referring to the seventh, 0.142857, which if you divide 7 into 1 is 1/7. I want to point out here on either side of this 369, these red lines and these green lines are perfectly tracing a seventh. And we end up never crossing the 3, 6, 9. We are paralleling it on every 1, 4, 2, 8, 5, 7, and back to 1. Notice how we're just paralleling. See that? But on the other side, we also have 1, 4, 2, 8, 5, 7, and back to 1. 1, 4, 2, 8, 5, 7, and back to 1. So we have the seventh perfectly paralleling the 3, 6, 9 hexagram that runs through the middle of the 24 wheel. I just thought that was amazing. Yeah. So I started studying the seventh. Where else is the seventh popping up? This is showing, this is all the same wheel. This is a smaller wheel showing the 3, 6, 9, 3, 6, 9, but it's also showing the seventh. 1, 4, 2, 8, 5, 7, 1. But it's also showing the triangles. Here's the 1, 7, 4 triangle. See the light green one? It's going to be doing an add by 6 in one direction and an add by 3 in another. 1 plus 6 is 7. 7 plus 6 is 13, but the 3 and the 1 come together to make the 4. 13 plus 6 is... Wait a minute. 4 plus 6... Yeah, either way. 13 plus 6 is 19, and the 9 and the 1 come together to make 10, which is a 1. Or 4 plus 6 goes directly to 10, which is a 1. And then it just keeps on repeating, where if we go the other direction, it's going to be add by 3. 1 plus 3 is 4. 4 plus 3 is 7. 7 plus 3 is 10, which reduces to 1. 1 plus 3 is 4. 4 plus 3 is 7. 7 plus 3 is 10, which reduces to 1. And that's the same for all of the triangles that are, that's how the triangles are doing math with each other. Sending messages back and forth, vibrations per second. Are we looking at the construction of the field? I don't know. But this Fibonacci sequence, both in the 24 wheel and in the 60 wheel, has turned into the most amazing magic puzzle I've ever ran across. This is just another diagram outlining the 1, 4, 2, 8, 5, 7, 1 in the 24 wheel. Oh, I was working on some logos. Because, see, once you understand, especially where the seventh is, look, we can look at this logo now. I don't have to mess it up with numbers. Why? Because I know it starts with a 3 here. So I can just say it's a 3, a 6, a 9, a 3, a 6, and a 9. I know exactly what those points are. And watch this. Since I know a perfect seventh runs in between them, I can go, the 1 is there, the 4 is there, the 2 is there, 8, 5, 7, 1. Because I know it doesn't cross. So I know where those notes. That's a 1, that's a 4, that's a 2, that's an 8, that's a 5, that's a 7, and it's back to the 1. So I found once you actually know what the numbers are doing as far as geometric shapes or reciprocals in the case of the seventh, and you realize how it's laying itself out, I thought, we don't need numbers. We can look at that, and we know exactly what we're looking at. We're looking at a continuous 3, 6, 9 pattern, doing math both ways, an add by 3 pattern one way, and add by 6 pattern the other way, and we're looking at a perfect seventh on either side of it. Yeah, 3 plus 3 is 6. 6 plus 3 is 9. 9 plus 3 is 12. And the 2 and the one of the 12 come together to make the 3. You know, or if we stay in 12, 12 plus 3 is 15, and the 5 and the 1 come together to make a 6, so we know that's a 6. Yeah. 15 plus 3 is 18, and the 8 and the 1 come together to make a 9. And 18 plus 3 is 21, and the 2 and the 1 come together to make the 3, which is right where we started. 3, 6, 9, 3, 6, 9. They're doing math, folks. Yeah, I thought of making this into a logo. I'd like to make, again, we don't need the numbers. You know, this one has the numbers on it, and that's really nice. You know, but then it makes it easier to see the 1, the 4, the 2, the 8, the 5, the 7, and the 1. But I don't know, that's, you know, shrink that down to make it a logo for my company. And once you see this video, you really don't need to know. You don't need to have numbers out there to know what this. What's that look like to you? What's that look like to you? It looks. I asked a nephew of mine, Nathan, and he said it looks like a black hole. Are we looking at does that look like a black hole? I look at it, and entropy is the first word that comes to my mind. But something is happening here with this arrangement. We're looking at some sort of a blueprint of the probably the submolecular world, I would think. I mean, this is nature. This is one of nature's patterns. Let's look at the 7th more closely. And my idea that mythology might actually have a numerical base, that God is one and rests on the 7th. We're talking 1, 4, 2, 8, 5, 7. And here's God right there. He's 1. It's his birthday. And he rests on the 7th. I don't know. But mathematically, since I've actually shown in these charts that the numbers, this is the 24 wheel, the numbers are using contraction to expand, and they're using multiplication to create spin. Like 4 plus 3 plus 7 is 14, and the 4 plus the 1 make the 5. This because this is in base 9. This is the 24 wheel. Okay, and the 6 plus the 5 plus the 2 is going to make 13, which come together to make the 4. And the 1 plus the 4 plus the 5 is 10, and there's your 0. 1 plus 0 is the 1. And then on the sideways, it's 3 times 2 equals 6. 6 times 2 equals 12. And the 2, of course, 12 is 3. 1 plus 2 is 3. 12. 12 times 2 is 24, and the 2 plus the 4 is a 6. Okay, so understanding, and the fact that when we jump up, we're going to do a review on the 60 wheel. The 60 wheel is doing exactly the same thing. It's using this exact same principles of expansion via contraction and diagonal doubling. But in the 60 wheel, it's in base 10. This is going on the back of a t-shirt. And if you want to study this, just buy the t-shirt with this on it, and you'll have your own. So we have a 24 wheel on the front of the shirt and that on the back of the shirt. I don't know. I want to wear these numbers myself. This, I was thinking of putting anything in the middle of this, like, you know, ET or something like that. Or, what do I got in here? Oh, for hang glider pilots, we could turn it into the Dog Mountain Free Air Force. Wouldn't that be cool? I like that. Anyway, we're going to talk about the 7th. Okay. And we're going to put out a hypothesis. Okay, this is just a hypothesis. The flower of life, if it is like a vibration or a consciousness, that the whole idea of it is that a single point, a 1, expands itself out as far as possible as far as it can reach. And then it goes to that point and it expands out again. And then it goes to that point and expands out again, and so on and so forth. And that is how it expanded itself. Well, let's take the numerical properties of 1, okay? And let's say that 1 plus 1 minus 10 plus 10, 100 minus 100. Let's say they're all the same. The zeros are merely placeholders, okay? So let's shave off 9 and throw 9 to either side. Let's put the 4 over there, and let's put the 5 over there. Let's do it the other, in every direction. We're going to reach out as far as we can and still maintain 1. So we take a 10 and we end up shaving off 9 and coming back to 1. Don't ask me how it's doing that, but I think that's what it's doing. And we have a 7 and a 2, which is 9. And we shave it off the other direction. We have a 8 and a 1, which is 9. Okay? And now, how is each one of these? Why did I pick the 7th? Well, it's popping up everywhere. And I found that using the same principle of contraction to expand, if we take, like, let's start here with the number 4. Okay, of course, this is 1/7. 1, 4, 2, 8, 5, 7. And we take the number 4, and let's subtract the numbers on either side. 4 minus 1 is 3. 3 minus 2 is 1. We have just recreated the 1 in the middle. If we take the 2 minus 4, we get minus 2. And minus 2 minus 8 is minus 10, which is 1. We have recreated the 1. 8 minus 2 is 6. 6 minus 5 is 1. There, we've recreated it on the positive side of the scale. It goes back and forth between negative and positive. 5 minus 8 is negative 3. See, we were in a positive one now. Now we're going to go to a negative one. Again, there's a definite balancing act going on here. 5 minus 8 is minus 3. And minus 3 minus 7 is minus 10, which is 1. 7 minus 1 is 6. 6 minus 5 is 1. 1 minus 7 is minus 6. Minus 6 minus 4 is minus 10, which is 1. See how in this configuration, whatever this principle is that allows the 1 to shave off 9 and remain a 1, you know, start with 10, shave off 9. How is it doing this? I don't know. But if that's a vibrational reality, with the numbers in this sequence of 1, 4, 2, 8, 5, 7, which is a 7th, can you see how it could reproduce itself to infinity? Yeah. Also, after I saw this, I thought, oh my gosh, it's also got some sort of other toroidal doubling pattern going on. If you even trace this red line, 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 14, and the 4, wait a minute. 4 times 2 is 8, 8 times 2 is 16. I can't do math. And the 6 and the 1 come together to make the 7. 16 times 2 is 32, and the 3 plus the 2 come together to make the 5. See that? 32, either 5 times 2 or 32 times 2. 32 times 2 is 64, and the 6 and the 4 come together to make 10, which resolves back down to 1. We have a doubling pattern going on here in a toroidal pattern. Interesting, because this same toroidal pattern, it pops out so many places. Let me grab a chart. I'm gonna okay. I'm gonna do this. I'll ruin this if I do it on this, but okay. Let's if we go in between. Yeah, I'm going to ruin it. No, I'm not. I might use it. Okay, let's do it this way. If we take the numbers in between the 3s, the 9s, and the 6s, notice how the 3s and the 6s arrange themselves on either side, and the 9s The Lucas sequence does the same thing, and the sequence known as Fibonacci sequences. The numbers arrange themselves so you will have the 3s on one side, the 6s on the other, if you do these 24 circles. Yeah, with any two numbers, pretty much, unless you start with a 3. If you can't start with 2, you can't start with like 3, 6, or the 3s, 6s, and 9s have to be separated. Yeah, you can't start. You can start with the 1, 2 right here. Everything you start with is a seed. That 1, 2 will recreate this entire wheel, and it'll put these numbers right where they are. You take a 5, 8 and start. 5 plus 8 is 13. 3, and in base 9 that's a 4. 8 plus 4 is 12. So in base 9 that's a 3. 4 plus 3 is 7. 3 plus 7 is 10. And on base 9 that's a 1. And 7 plus 1 is 8. You'll recreate this entire sequence perfectly, no matter which seed you choose to draw from. Take the 6 and the 4. Take the 4 and the 1. It'll work. But what I did notice is between this 3 and this 9, that's a 4, right? 2 plus 1 plus 1 is 4. Let's go over here. Between this 6 and this 9, 2 plus 8 plus 1, 8, 9, 10, 11, which is a 2, okay? So let's put a 2 up in that corner. Off here to the side, between these 6s, we have 5 plus 1 plus 4, which is 10, which is a 1, right? Okay. Down here at the bottom, right. Down here between the 6 and the 9, we have 8 and 8, which is 16, plus the 7 is 23. 23 is a 5. The 3 plus the 2 come to be a 5. And between this 3 and this 9, we have 7 plus 1, which is 8, plus 8, which is 16, and the 6 and the 1 is a 7. Okay. I missed out on an 8 somewhere. Oh, this one off to the side. I haven't done this one yet. Okay. 9. 5 plus 4 is 9, plus 8 is 17, and the 7 and the 1 come together to be an 8. So we have just done 1, 4, 2, 8, 5, 7, back to 1. Look at that toroidal pattern. It's in the numbers in between the 3, 6, 9. If you contract them together, we get this same 1, 4, 2, 8, 5, 7, 1, 4, 2, 8, 5, 7 that we're finding right here and right here. 1, it's just in a little bit different configuration. 1, 2, 4, 8. 1, 4, 2, 8, 5, 7. We're getting, okay, what we have here is a circle. We're getting, as this toroidal pattern, exact same toroidal pattern when we did the doubling sequence. 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, etc. It might be nothing, it might be something. So I just thought I'd mention everything that I see, and let's continue. There's a lot of material to cover. Properties of the 7. These are just some basic facts. All mathematicians know this. 7 times 2 to the first power is 14. 7 times 2 to the second power is 28, etc. But what you do, 7 times 2 to the sixth power, 7 times 2 to the seventh power, 128 times 7. And you bring it over here and write it there. And you write these in columns and then carry them down, and you end up with 1, 4, 2, 8, 5, 7, 1, 4, 2, 8, 5, 7. It repeats itself. Yeah, even including the remainders. It's pretty cool. 7's a very, some more properties of 7s. Between 1 and 10, there's one number divisible by 7. Between 1 and 100, there's 14 numbers divisible by 7. Between 1 and 1,000, there are 142 numbers divisible by 7. Look what's happening here. Again, 7 and 7th. It's a freaky number. That's all I got to say. This, I got to give credit to a couple fellas I think did a marvelous work on their book, which is right here. God, you guys, I got your book right here. Here it is. This book. Robert Edward Grant and Talal Ghanem, PhD, Philomath, the geometric unification of science and art through number. And I stole this drawing from right here. Right here. This book is, oh, and also I learned a lot about the Lucas sequence from you guys. More than I knew. And anybody who wants to dive into, I'm not, if I share something from this book, I'm going to let you know. And this is one of the things. I had not seen this myself. So thank you guys. I think it's pretty cool how I just showed you that these numbers are actually recreating the 7th. This would be the 4. You know, this would be the 8, 9, 10, 11, the 2. Down here, the 5, 1, and the 4 would be the 1. That'd be the 10. So here we got 1, 4, 2, 8, 5, 7, and back to 1. Well, in the same circle, in Philomath, he makes it very clear that between these digits, if you just add the numbers from here to here, you recreate the 6. If you add the number from here to here, you recreate the 3. If you add the numbers from here to here, you recreate the 9. If you add the numbers from here to here, you recreate the 6. And they're even offset. See? Yeah, we have in this inner ring, we have a 3, 6, 9 there. Over here, it's 3, 6, 9, almost like the shifted opposite directions. This is very cool. Oh, we already did this. So these charts, we already went over how they're, and then now we're going to jump into the 60 wheel. We're going to get back into prime numbers because it's in the prime number, it's in the 60 wheel. This is the wheel that really got my attention about prime numbers. Before we go any further, I want to show you something I do on all these algorithms, okay? I get out some graph paper, okay? Like the 24 wheel, okay, which we just looked at. It's this one, okay? This is the 24 wheel, okay? I will put it on graph paper, move 1, turn right, move 1, turn right, move 2, turn right, move 3, turn right. I want to see if this is a program and returns to X. And indeed it does. You start at X right here and turn 1. Go 1, turn right, go 1, turn right. Here's 2, turn right, go 3, turn right. Go 5 in the red, turn right, go 8 in the red. And that's right here. You know, and then you turn right again, and the remember how the 8 and the 5 are a 13, but the 3 and the 1 come together to make the 4. We're using the reduced sums. So you go 1, 2, 3, 4, turn right again, go 3. You follow this perfectly. You will come back this way to X, and then remember how we talked about then the 8 plus the 1 turns into a 9. And so this 0 becomes a 9. That happens right here. So now you have to go 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And start over again. Turn right 1, turn right 1, turn right 2. And what's so cool is you are going to recreate an identical cell that is going to perfectly knit along these 4 corridors with the cell you just did. I know. The only places they touch, they are actually perfectly knitting into each other. Let's see, right there and right here. Yeah, I think so. I know, that's pretty cool. I don't know. And then the same thing will happen. You go around here and make theirs, and then you're going to turn right, and you're going to go off 1, 2, 3, 4, 5, 6, 7, 8, 9 again, and then this one is going to knit itself into this one, and it's just going to keep on moving over. I know. So I checked this on all, like the entire 60 wheel. Jane has done this on his site, Jane 108. And actually, Jane puts out a lot of awesome workbooks, mathematics for juniors, keen teens, and adults. And the entire 60 wheel is in here. Jane, it's right here. Jane will teach you how to make it, and he's got all the Fibonacci numbers written out. They're full length here. The first 24, the second 24, and then this is the workbook that I obviously didn't do, but I like it, where he gives you the opportunity to take the 7th number, which is 13, and the 3 and the 1 is a 4, and you digitally reduce them, and you'll find out that all these numbers are exactly the same as all these numbers. And that you need to go through a little exercise like this. List the first 24 Fibonacci numbers. List the second 24 Fibonacci numbers. Okay, reduce them all to the single digits we're talking about in base 9, and you'll find that these columns are identical. And you'll find actually that if you even take the next 24 Fibonacci numbers, they will also be identical to infinity. Now, are these 24 a complete circuit? They seem to be. You start there and you go through all. Oh, we're in the 60 wheel now. We're in this wheel right now. We're in this wheel right now. So is this is the last digit of the first 60 Fibonacci numbers. Is it also a sequence? Yes, it is. You'll go through 60 moves here, and you'll come back and land exactly where you started. But not only that, I test all the breakdowns of like the icosagon compared to the icosagram. They're all circuits. I take the number sequences of how the every 9 icosagon, which we're getting into that right now. The every 9 icosagon, it's in here. It's my fave. There's so much going on in it. Here, this one right here. The every 9 icosagon. Okay? What I do is I take the order in which this icosagon is made. The 0 to the 4 to the next 4, which is 9 moves. That 4 to that 4 is going to be 8, which is 9 more moves. That 4 to that 8 is going to be 12. But we're in base 10 now. So you drop the 10 category, and there it is right there. So what I do is I get out the graph paper and break it all down. Starting with a 0, we go to the 4, 4, 4, 4, 8, 8. I map out the entire sequence that this every 9 does as it separates the even numbers from the odd numbers, which I'm hypothesizing are then becoming our prime number system. I think it's given us the basis for the primes, but that's a hypothesis. But I check it out this way, and when you hit a 0, just don't move. You skip the zeros and go to the next one. So in 16 moves, not counting the zeros, this came back to X. But not only that, I do all the other sequences too. Like this one is the sequence of the 20-pointed star that is created in the middle of this. I went from the 8, see 8, 8, 6, 4. That would be, let's see, 8 to the 8, 8 to the 8, to the 6, to the 4. So I must have started right there. See, 8, 8, 8, 8, 6, 4, 0. So I probably started 8, 8, 6, 4, 0. It's hard to keep track of where they go. And then 4 plus 0 is 4. So I wrote all those numbers down in the order that they interconnect. and did this, and sure enough, in 16 moves, skipping all the zeros, it comes back on X. So both this outside ring is an obvious, some sort of a constantly repeating program, and the inside ring is a constantly repeating program. And I do this to all these mathematical shapes, and they almost all prove out to return to X. The only exception would be the cubes. Ironically, do not return. When you put the cubes on graph paper, they shoot off into space. But everything else returns. Anyway, that is this is kind of a. I got to show you something. I first drew this on my window. The every 9. This every 9. Like I am a madman. This is the every 9 spiral. This is how the every 9 spiral. I first did it on my window. It's still up there. Okay. I can't put all that on the back of a t-shirt. This is the first time I figured out the every 7 spiral. It's still on my window too. Adds together every 7 digits, then returns in 7 revolutions. So my goal was like, how do I put it and make it very clear as to what it's doing without too much of a mess? And this is the best I've been able to come up with so far. Maybe you can do better, and I'd like to see. The goal is to come up with designs that illustrate the math that these geometric shapes are performing. Okay. Let's keep going. Got a lot. There's a lot. No, there's a lot more. Remember how we touched on this, how when I separated these 3 from these 2, from these 3, just groups of 2s and 3s, I was just goofing off, and it ended up being 2 more complete add-by patterns. If you bring the 2 and the 9 down here, 9, 10, 11 becomes a 1, because we are in base 10. Yes, this is the 60 wheel. All these numbers here are the numbers in the 60 wheel. 0 plus 1 is 1, 1 plus 1 is 2, and it goes all the way around, and then instantly repeats when it hits 61. So your 61st number, the last digit is going to be 1. Your 62nd number, the last digit is going to be 1. Your 63rd number, the last digit is going to be 2. And Google it. And in the Fibonacci sequence. And then at 120, it's going to start repeating again. At 180, it's going to repeat again. So, and then at 300, the last 2 digits start recounting this sequence. It's like a big clock. But then as I separated these, even broke up the sequence itself, 1 plus 3 is 4, 3 plus 4 is 7, 4 plus 7 is 11, and since we're in base 10, we drop the 10 category. 7 plus 1 is 8, 8 plus 1 is 9. And the same way on the outer ring, 4 plus 2 is 6, 2 plus 6 is 8, 6 plus 8 is 14. Drop the 10 category. I have a hard time shifting back and forth between base 9 and base 10. And that's my excuse. I'm sticking with it. But then in our last episode, this is not a primary icosagon. This is a primary icosagram, because grams have points, gons have sides. Okay, but I wanted to point out how it is separating the even digits from the odd digits. Okay, moving right along. Also, at the same time it's doing that, it's every geometric shape I've been able to come up with is doing some sort of mathematical function. The stars of Solomon, which are unicursal, because you can do them with one finger and never take your finger off the paper. And this is a gram, not a pentagon. See, I get all mixed up. I like the mistake on there. It makes it. I think crossing off the gon. I'm going to leave this. I would put this on the back of a T-shirt with the mistake. I'd sign it. It's like Burton original. And how depending on the direction of rotation depends on what kind of math you're doing in the stars, whether you're adding by 8, adding by 2, adding by 4, adding by 6, depends on rotation. If you pick a star where you're adding by 2 in this direction, like 2 plus 2 is 4, 4 plus 2 is 6, 6 plus 2 is 8, 8 plus 2 is 10, drop the 10, 10 plus 2 is 12, and you're back to the 2, it's going to be adding by 8 in the opposite direction. 2 plus 8 is 10, 8 plus 0 would drop the 10, and then 0 plus 8 is 8, and 8 plus 8 is 16, and 16 plus 8 is 14, drop the 10 category. Oh, wait, 16 plus 8 is 24, excuse me, drop the 10 category, and 4 plus 8 is 12, and I'm terrible at math. I made this as a wedding gift for my nephew and his lovely wife. And I think I wrote stuff on the back. Yeah, I did. Okay. And it just illustrates again what the the hexagram. This is a unicursal pentagram, pente for 5. And this is the same thing. This is showing how it's adding by 6 in this direction. It's adding by 4s in this direction. But this is also showing what the pentagon, which is the sided object, is doing. It's adding by 2 in this direction. It's adding by 8 in this direction. 2, 4, 6, 8. Who do we appreciate? Whoever put this amazing magic puzzle together that we live in. This is how the world is assembling itself. And look at all these different geometries it's creating mathematically at the same time, superimposed. They're all on top of each other. On top of this, right on top of this, you've got cubes doing times 3 in the counterclockwise direction. 1 times 3 is 8. 8, excuse me. 8 times 3 is 24. And we're in base 10, so it's a 4. 4 times 3 is 12. There's your 2. 2 times 3 is 6. 6 times 3 is 18. All these cubes and all that mathematical action is happening at the same time. At the same time, we have this every 7 function going on in the counterclockwise, where if you move every 7. Oh, so how many add-togethers do we have now? By the way, it also adds every 5 in the. If we add every 5, look at this: 1, 2, 3, 4, 5. But it's on a 5, and we're just going to get 5s and 0s, but it still works. If we start from the 1, 1, 2, 3, 4, 5. 1 plus 8 is going to be 9. 1, 2, 3, 4, 5. There it is. Okay, 8 plus 9 is going to be 17 in base 10. 1, 2, 3, 4, 5, and there's your 7. 7 plus 9 is going to be 16 in base 10. 1, 2, 3, 4, 5, and there's your 6. It's adding every 5 in this direction. It's adding every 3 in this direction. If you start from any of the points created by the every 9 spiral, you have to start. The every 3 is limited. It's limited to these points, these even integers. You have to take off from an even integer, or the every 3 does not work, which makes it really intriguing. Why? But it does. And so if we start at one of the evens and go 3, 1, 2, 3, and we have 1, we have 0 and 2, which is going to be 2. 1, 2, 3. We have 2 and 2, which is going to be 4. 1, 2, 3. We have 2 and 4, which is going to be 6. 1, 2, 3. And so on and so forth. And it does this, it adds together every 7 for 7 revolutions. 4, 3, 2, 1. And at the end of the 7th revolution, it will have landed on every single digit one time only, and then it lands back where it started, and then it starts over again. I know. it's doing that all at the same time. The every 9 spiral is sifting out the prime numbers from the even numbers, or the odd, let's just say odd numbers. Odd numbers, these are all primes and semi-primes though, no matter how you hook them together, they end up being primes and semi-primes as far as what I've, like 17, definitely a prime. 19, there's a prime. 99, definitely a semi-prime. It's a composite of 9 and 11. Same way with a lot of these are semi-primes. But notice, this got my attention, that got my attention, and the every 7 spiral got my attention, because 7 is a prime. The every 3 going this way, 3 is a prime. The every 5 going this way, 5 is a prime. The only one that's not a prime is the every 9. The every 9 icosagon, which created this whole mess, is not a prime. That created this 20-pointed star going every 9, every 9. 0 plus 4 is going to be 4. 4 plus 4 is going to be 8. 4 plus 8 is going to be 12. That's going every 9, and it does it in it. But 9 doesn't go into 60, so it goes beyond it, and you end up landing on all the other ones too, that make up this one star. And other than the every 9, I'm looking at prime numbers here. Even 1's a prime, really, and we know every 1 adds together. 1 plus 1 is 2. 1 plus 2 is 3. So we got that. We got every 3 this direction. We got every 5 this direction. We got every 7 this direction. So I thought, oh my gosh, let's try the next prime. Let's try 11. Let's try 11 in this direction. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's a 4. 0 to a 4, so in 11, if it goes this direction, it should be a 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's got a 7. So let's try 11 in this direction. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's a 9. 0 and a 9 should be a 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's a 9. 9 plus 9, 11 more, should be 8 for 18. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2. Oh, we're doing 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There it is. There's the 8. It works if you know how to count. If you don't know how to count, it's a little tough. And so what I've found is every 11 does the same thing that the every 7 does. And it ends up landing on every digit one time, and in 11 revolutions comes back to where it started. I'm serious. So that brings me back to prime numbers. What's going to happen when we do the 13? Well, I've done the 13. I've done the 19. I've done the 17. And I've come up with this list. I'm calling them the angel numbers. Every 7 for 7 revolutions. Every 11. Remember, we tried it this way, it didn't work. Every 11 this way for 11 revolutions. Every 13 this way for 13 revolutions. And I haven't checked all these. I haven't checked every 17 for 17. That's a lot of counting. If you want to help me on this, I think I've done enough that this is going to hold. But I have not done every 53 for 53 revolutions. I have not done every 29 for 29 revolutions. I have done every 43 for 43. So get out your pen and paper, and if you want to help me, if you're as much of a geek as I am, go for it. But from what I've done so far, it looks like not only is the every 9 spiral separating the evens from the odd numbers, the evens from odds. Prime numbers are doing something special in this wheel. Prime numbers have, and we haven't got to the end of this yet. I just discovered this last week. And then I went into the library and I just wanted a printout of all the Fibonacci numbers, in order. I mean, and they get really I mean, look at some of them. That's a Fibonacci number. Yeah. What I thought was interesting about this printout from the library is how they were kind enough to list which Fibonacci numbers were primes. Okay, but then I noticed, well, wait a minute, it falls on Fibonacci on number 29. The 29th Fibonacci number is also prime. That's interesting. And then this Fibonacci number, 28,657, falls on 23. Really? Seriously. And then this prime, 1,597, falls on 17. Is this a joke? Seriously. And this prime, 233, falls on 13. Okay. And the next prime number is 89 and falls on 11. Oh my God. The next prime number is 13, and it's number 7. The next prime number is 5, and it's our 5th number. Finally, 3 falls on a 4. Phew. And this. I have a lot of counting to do, and if you want to help me, I really can't justify putting this on the back of a t-shirt until I've counted all the rings and confirmed that this is actually correct. All right. But primes do this other thing where in the 24 wheel, they fall on the lines of a Maltese cross. This is known, but then since I found this in the Philomath book, actually, thanks guys, I found it in this book. I found the Maltese cross. It's in here somewhere. Forget where. I decided to make a wheel of 60 digits, starting with 1, go all the way around to 60, and then jump up here to 61 and 62, 63. And I noticed the prime numbers line themselves up in balanced sequences of 2, 1, 2, 2, 1, 2. Look at that. In these radiant, what are we looking at here? I just highlighted the prime numbers. And the ones in between are indeed semi-primes, which are numbers that are composed of prime numbers, if I get the definitions right. Let me find a low example, like this one, 77. That's a composite of 7 and 11, which are both prime numbers. It's in the line with the primes, but it's not. I didn't highlight it because it's not a prime. It's actually a semi-prime, I think. Fascinating. Okay. So next week, or next time I do this, we're going to get into the dodecagon and the unicursal dodecagon and in all its functions. And I want to do a shout out to a gentleman out there who made a drawing very similar to this. And I think he was on the verge of finding the math inside this shape, because this shape is definitely doing a whole lot of math. And yeah, it probably does have something to do with the zodiac, the 12 points. Yeah, probably does. Probably has something to do with the stars. I don't know. I'm not an astrologer. But I've seen online where someone took this fellow's drawing, and the fellow's name was Brian Raymond Payne, and he made a drawing very similar to this. But he made an observation about the degrees. I'll have to look up the video again. But I tried to find Brian online, and I think he's passed away. I found an obituary for Brian Raymond Payne that loved to do mathematics, and I don't know if it's the same guy. But I hope not. If the guy who made this kind of drawing, and his name's Brian Payne, is still alive, let me know if you've passed on. Good work, brother. You were right on the edge of this, and I saw you posted something like this in 2015, and it looks like you passed away in 2019. But we'll get into this next time and exactly what this one's doing, and. So I think that's all I wanted to share this time. That's a lot, I know. Well, thanks for hanging out. And if you like it, give it a thumbs up. Don't forget to subscribe if you want to see more of this. I think it just keeps coming. I think as I share this, honestly, I didn't know all this about the prime numbers before I started trying to share all this. And as I've been putting this together to try to share it, this whole thing about the prime numbers is popping out of this sequence like crazy. There is wispies and thermals going off all around me here. Can you see them? Every once in a while they form into a really big one. Oh, this is fantastic. Jeremy's over on the edge. Mount Rainier's just over the trees. It's a beautiful morning.